There is a number in physics that should not exist. It is the distance to the nearest copy of you. Not a metaphor. An actual, calculable distance to a region of space containing a person identical to you, atom for atom, reading this exact sentence. Some cosmologists have put that number on paper. It is unimaginably far. But it is finite. And the strange part is this, that calculation does not come from science fiction. It comes from taking our current best theories completely seriously, and refusing to stop when the answers get uncomfortable. The multiverse is not one idea. It is at least 4, and they are widely different from each other. Some are nearly unavoidable consequences of mainstream cosmology. Others sit at the far edge of what we can even call science. Most people mix them all together into one word. So let's separate them properly. For levels, in order of how strange they get. And by the end, you'll be able to say exactly which multiverse someone is talking about, and how seriously to take them. First, what actually counts as a multiverse? The word suggests other universes sitting next to ours, like rooms in a hotel. That picture is almost always wrong. In most versions, there is only one thing, one reality, and it is simply far larger or far stranger than the piece we can see. We are not in one room among many. We are in one small, well-lit corner of something enormous, and the light hasn't reached us from the rest of it. That corner has a name. It's called the observable universe, and it has an edge. Level 1. The multiverse beyond the horizon. Light travels at a finite speed. The universe has a finite age, a little under 14 billion years. Put those two facts together and you get a hard limit. There is a maximum distance from which light has had time to reach us. Beyond that boundary, there could be anything, and we would never know, because no signal from it has arrived yet. That boundary is called the cosmological horizon. Because space itself has been expanding while that light traveled, the observable universe is far wider than 14 billion light-years. It's roughly 93 billion light-years across. But here's what matters. That horizon is not the edge of reality. It's the edge of our information. It's a limit on us, not on the universe. So what's past it? Every measurement we have says more of the same. The universe looks flat, and it looks uniform on the largest scales, in every direction. If that pattern continues, space may simply keep going. Possibly forever. And infinity does something very strange to probability. A finite volume of space can only be arranged in a finite number of ways. There are only so many particles, in only so many configurations. So if space is truly infinite, and matter keeps arranging itself, then every possible arrangement doesn't just happen once. It happens infinitely many times. Which means somewhere out there, the arrangement that makes up this room, this planet, and you, occurs again. Not as a copy in another dimension. Just far away, in ordinary space, obeying the exact same laws of physics. The cosmologist Max Tegmark once estimated how far you'd have to travel to find your nearest duplicate. The number is so large it has to be written as a power of a power. But it is a number. That's level 1. No new physics. No extra dimensions. Just space, continuing. If it makes you uncomfortable, that's reasonable. But notice what it would take to avoid it. You'd have to argue the universe stops somewhere. And we have no evidence that it does. Level 2. Bubble universes. This one comes out of inflation, our leading explanation for why the early universe looked the way it did. The idea, developed in the 1980s by physicists including Alan Guth and Andret Linder, is that the infant universe went through a brief, violent period of exponential expansion. Space doubled, then doubled again, unimaginably fast. Inflation solved real problems. It explains why the universe looks so uniform, and why it looks geometrically flat, and it predicted the pattern of tiny temperature ripples we later measured in the cosmic microwave background. That prediction-matching observation is a large part of why cosmologists take it seriously. But inflation has an awkward property. In most versions, it doesn't stop everywhere. It stops in patches. One region stops inflating and settles down into a calm, expanding universe like ours. But the space around it keeps inflating faster than the calm regions can spread. So it never fully ends. It just keeps producing pockets. This is called eternal inflation. And each pocket is a bubble universe. Now the important part. Different bubbles can settle into different states, and when they do, the physics inside them can differ. Not the deep mathematical laws, but the constants. The strength of gravity. The mass of the electron. How much dark energy there is. String theory makes this worse, or more interesting, depending on your temperament. It suggests there may be an enormous number of possible stable configurations, a landscape of possibilities, with estimates often quoted around 10 to the 500th power. Most of those universes would be dead. Get the constant slightly wrong and stars never form, or atoms never bind, or the whole thing recollapses. And that's the uncomfortable idea at the center of level 2, maybe our universe isn't finely tuned for life because someone tuned it. Maybe there are simply vast numbers of untuned universes, and we necessarily find ourselves in one of the rare ones where observers can exist. That argument is called anthropic reasoning, and physicists genuinely disagree about whether it explains anything or just restates the problem. Level 3. The many worlds of quantum mechanics. This is the one people usually mean, and it is the most misunderstood. Quantum mechanics is the most precisely tested theory in the history of science. Its equations work perfectly. The trouble is what they seem to say. Left alone, a quantum system evolves smoothly into a combination of possibilities. A particle isn't simply here or there. The mathematics describes it as a blend of both, and that blend produces effects we can measure in the laboratory. But when we actually look, we never see a blend. We see one outcome. The standard textbook response is that measurement collapses the possibilities into one result. But nothing in the equations describes that collapse. It's added by hand, because it matches what we observe. In 1957, a graduate student named Hugh Everett proposed removing it. What if nothing collapses? What if the equation just keeps running? Then when you measure a particle, you don't select one outcome. You become entangled with it. The version of you that saw result A and the version that saw result B both exist in the mathematics, and they stop being able to influence each other. That separation process is called decoherence, and it's real, measured physics. So the branches don't fly off to other dimensions. They're all in the same wave function. They simply lose contact. Notice what Everett actually did here. He didn't add worlds to the theory. He removed a rule, and the worlds were what remained. To this day, that's the strongest argument in its favor. It's the simplest reading of equations we already trust. The strongest argument against it is that it multiplies reality beyond anything we can test, and that nobody has fully explained why probabilities work out as they do when every outcome happens. Serious physicists sit on both sides. It is not settled. Level 4. The mathematical universe. This is the deep end, and I'll be honest about that up front. Every level so far still assumed there is one underlying set of mathematical laws. Level 4 asks why those laws, and not others. Tegmark's proposal is that there is no reason, because every mathematically consistent structure exists, and physical existence is nothing more than being such a structure. Our universe isn't described by mathematics. Under this view, it is mathematics, and so is every other possible one. It's an elegant answer to why anything exists at all. It's also almost impossible to test, and many physicists regard it as philosophy wearing a lab coat. I'm including it because it's the honest end of the ladder. It's what you get when you keep asking, but why these rules, until there's nowhere left to stand. Now, 2 ideas that don't fit the ladder but keep coming up. The first is the simulation argument, formalized by the philosopher Nick Bostrom in 2003. His actual claim is narrower than people think. He argued that at least one of 3 statements must be true. Civilizations almost always go extinct before they can run detailed simulations of minds, or they can, but choose not to, or we are almost certainly living in one. It's a logical trilemma, not a claim that we're in the Matrix. And it's worth noting it isn't really cosmology. It's an argument about statistics and consciousness. The second is stranger and more physical. In 1992, the physicist Lee Smolin proposed that black holes might give birth to new universes on the other side of their singularities, with slightly different constants. If true, universes that make lots of black holes would produce lots of offspring, and the population would evolve toward whatever settings make black holes efficiently. Since the same conditions that build black holes also build stars and heavy elements, life might be a side effect of a universe optimized for something else entirely. It's speculative. But unlike most of this list, it makes predictions that could in principle be ruled out. So is any of this science? That's the real fight, and it's worth ending on honestly. In 2014, the cosmologists George Ellis and Joe Silk published a piece in Nature warning that theories which can't be tested risk breaking the boundary between physics and philosophy. Their concern was straightforward: a theory that explains any possible observation forbids nothing, and a theory that forbids nothing is hard to call science. The counter-argument is that we don't get to choose what our best theories imply. Nobody set out to invent a multiverse. It fell out of inflation, and it fell out of quantum mechanics, and refusing to look at it doesn't make it go away. Here's where that leaves us, honestly. Level 1 requires only that space keeps going. Level 2 follows from inflation, which we have real evidence for. Level 3 follows from taking quantum mechanics literally. Level 4 is a philosophical position that may never be testable. They are not one idea, and they deserve very different levels of confidence. Anyone who tells you the multiverse is proven is overselling. Anyone who tells you it's obvious nonsense hasn't looked at how naturally it falls out of theories that work. What's remarkable isn't that these ideas are strange. It's that they came from carefully measuring the sky, and following the mathematics honestly, even when it led somewhere no one wanted to go. The universe never promised to be the size we find comfortable. I'm Redshift Hour. There's a new one every week.